Every time a rocket launches, it's not just fire and thunder. It's one of the strongest forces in nature, Earth's gravity. To truly relieve Earth, a rocket has to reach astonishing speed of 11.2 km per second. That's more than 40,000 km per hour. And here is the crazy truth. More than 90% of the rocket's weight at liftoff is fuel. Now comes to cruel truths. Even if you can reach to that speed, the rocket equation makes things much harder. Earth's gravity pulls everything with an acceleration of 9.8 meter second square. To escape permanently, you need escape velocity given by the formula. If we plug in the numbers, we have this velocity. That's the minimum speed to escape Earth's gravity without an extra thrust. On the Moon, escape velocity is just 2.4 km per second. On Mars, it's 5 km per second. This is why launching from the Moon would be far easier. Earth is the real monster. The real challenge comes from Tsiolkovsky's rocket equation. The delta V, the total change in velocity required to reach orbit. The velocity of exhaust, velocity of gases, 3000 meters per second for chemical rockets. M0 with initial mass, rocket plus fuel plus payload, and the final mass, rocket after fuel is gone. Suppose a rocket engine has exhaust velocity of 3,500 meters per second and we need delta V of 9,400 meters per second to reach low Earth gravity. This is the huge ratio. If you keep all the empty tanks, the rocket becomes dead weight. So how do we fight back? With the staging. In a multi-stage rocket, empty tanks are dropped and only the fuel section continues. This resets the mass ratio, making the rocket far more efficient. Like Saturn V, at liftoff, it weighed more than 3,000 tons. After stage 1 separation, rocket was already much lighter yet still accelerating. By the time the third stage, only 140 tons remained, about 5% of the original weight. Without the staging, the Apollo mission would have been impossible. Why exhaust velocity matters? When it comes to rockets, fuel is everything. The type of fuel determines how much thrust you can generate and how efficiently you can reach orbit. In Tsiolkovsky's equation, the key parameter is exhaust velocity, which depends on the propellant type. The solid rocket fuel, which also space shuttle boosters used, had 2,500 meters per second exhaust velocity. Simple, powerful thrust and reliable. Cannot be throttled or shut down, and it's not so efficient. Like the space shuttle used 2 giant solid boosters alongside its main liquid engines to provide the raw thrust needed to escape Earth's atmosphere. Liquid rocket fuel RP-1 plus liquid oxygen, which used in Falcon 9, the first stage, exhaust velocity over 3,000 meters per second. The dense fuel, high thrust, efficiency lower than hydrogen. The third one, liquid hydrogen plus LOX, which used in Saturn V's second and third stage, Artemis SLS. The exhaust velocity over 4,400 meters per second, one of the highest for chemical rockets, very efficient, lighter molecules, higher exhaust velocity, and needs extreme cryogenic storage at minus 253 degrees, low density. Like the Saturn V's second and third stage use LH2 plus LOX, giving the rocket the efficiency needed for lunar missions. This fuel combination shows why different fuels are used at different stages. dense fuels like kerosene solids at liftoff, and high-efficiency fuels hydrogen once above the atmosphere. Why escaping Earth is so hard? Every launch fights three invisible enemies: gravity losses. The rocket must fight against being pulled back during ascent. Atmospheric drag. Air resistance costs hundreds of meters per second in velocity. And last, rocket equation limitation, the exponential relationship between mass and velocity. That's why launching costs over 10K per kilogram. Historically, though SpaceX has reduced around 2,000 per kilogram. Gravity is tough, but curiosity is stronger. Subscribe, hit the bell, and fuel up for more mind-blowing science and space discovery coming your way.